Welcome to our final installment of Lecture 2. So we're at Lecture 2J. I apologize for there being so many parts to this particular lecture, but it's just the way that the material broke out. So this last part is still continuing on with chemical reactions, and this is a very special type of reaction called oxidation reduction reactions. And this is a type of reaction that we will also go in more detail in the very last lecture of the course. And so we'll just get into it a little bit here, and we'll get into a lot more when we do our electrochemistry in week 6. But let's go ahead and get introduced to oxidation reduction reactions. So if you go back and look at all of the reactions we've done so far, really the only type of reactions that we've had has been where our reactions have had ions exchanging partners. When you're doing oxidation reduction or redox reactions, instead of ions changing places, what you have is you have electrons moving from either ion to ion, atom to atom. It just depends on what species are present. So let's take a look at a reaction here. So we have iron plus copper sulfate going to iron sulfate plus copper. Now when we write it as that complete molecular equation up top, it's hard to see that we've had electrons changing partners. But if we break apart the aqueous species, we end up canceling the sulfate ions, the SO4s, and now we can really see where electrons moved from one atom to another. So we see here in our reaction, our iron went from being iron in a zero oxidation state, so a solid, to a 2 plus. Well, to go from 0 charge to a 2 plus charge, it must have lost 2 electrons. Well, electrons can't just disappear during the course of a reaction, so they must have gone somewhere. Well, if we look at the copper went from having a 2 plus charge to being a solid with a 0 charge. And so that means that the copper must have picked up 2 electrons. And so the electrons went from the iron to the copper ion. So it went from the iron atom to the copper ion, and we ended up with an iron ion and a copper atom. Okay, so in order to track that movement of electrons in more complex systems or complex reactions, we've developed a concept called oxidation states or oxidation numbers. So one of the things that we have to do is learn how to assign oxidation states or oxidation numbers to our various atoms, ions, in an entire reaction. So you don't just assign an oxidation number to a molecule, you have to assign it to each individual atom that takes place that's taking part in a reaction. That's the way I want to say that. Okay, so we follow these rules, and again, we want to follow these in order because some of these are order dependent. Okay, so if you're looking at a reaction, anything that has an elemental form, so solid iron, solid copper, H2 gas, O2 gas, that's their elemental form. So we would assign that an oxidation state of 0. So it would have an oxidation number of 0. If we have oxygen that is in a compound, very important, in a compound, we assign it a -2 oxidation state. Unless you have a peroxide where 2 oxygens are joined together, then you assign it a -1. Those are fairly rare. You don't see them very often at this level of chemistry, but if you move on to higher levels of chemistry, you can certainly see peroxides as they're very common reactants because they react very strongly. If you have any hydrogen that's in a compound, you will assign it a +1 oxidation state. If you have any group 1A elements, sodium, lithium, potassium, present in a compound, you will assign it a +1. If you have any group 2A elements, calcium, barium, magnesium, you assign those a +2. If you have a monatomic ion, you're going to assign an oxidation state equal to its charge. So a monatomic ion would have been like the iron and the copper that we saw in that previous reaction, where you have an iron or an ion all by itself with nothing attached to it. So but it has a charge. It's not an element. If it has a charge, you give it an oxidation state equal to its charge. Now, if you have a compound and you've assigned oxidation states to all of the atoms in the compound, the sum of all the oxidation states have to be equal to the charge on the ion or molecule. Now, you can use this rule in one of two ways. You can use it to check to make sure that all of your oxidation states add up to the charge that's given, or if you have something that does not have an oxidation state, but you know all of the others, then you can find what the oxidation state of that particular element must be, because you know that everything has to add up to the charge on the ion or molecule. Now, sometimes that's still not enough. Every once in a while you'll have a halide, bromine, chlorine, fluorine, in a compound that hasn't been assigned an oxidation state, as well as maybe a metal that's in there. If that's the case, then you can assign that halide a -1, and then go back and go back to rule number 7 and see if there's anything else that needs to be assigned. Okay, it's important that you assign that oxidation state of a halide as a -1 only as a last resort. This is why it's important to follow these rules in order. So let's look at an example here. So here is calcium chloride. We have calcium metal plus chlorine gas forming calcium chloride, CaCl2. Is this a redox reaction? Well, in order to find out, we assign oxidation numbers by applying the rules in order. So let's go through and do that. So do we have anything in an elemental state? And the answer is yes, we do. We have the calcium that's present as a solid. We know it's a solid because it has no charge and nothing attached to it. So that's just going to be the atomic form or the elemental form of calcium. So we're going to assign that an oxidation number of 0. And we also have the chlorine, Cl2. Chlorine is a diatomic molecule in its elemental form, and so Cl2 gas is in fact its elemental form. So we're going to assign that a 0. Okay. Do we have any oxygen in a compound? No. Do we have any hydrogen in a compound? No. Do we have any monatomic ions? No, we don't have those. Do we have any group 1A elements in a compound? Nope. Do we have any group 2A elements in a compound? Yes, we do. We have calcium. Calcium is in a compound in the product, so we're going to assign that a +2. Okay, and then we have that the sum of all of the elements within a compound have to equal the overall charge, or the sum of the oxidation numbers. We don't know our chlorine here. I've got 2 of them, but I know that +2 plus something has to equal 0 because there's no charge in that calcium chloride. So the total sum charge of the chlorines must be a -2, okay, but there's 2 of them, which means that each chlorine is a -1. Okay, so the oxidation number of chlorine in calcium chloride is -1. Okay, so we've assigned our oxidation numbers. The next question we want to ask ourselves is, did anything change oxidation state? And if so, then it is a redox reaction. Notice that the calcium went from a 0 to a +2. The chlorine went from a 0 to a -1. So we did have things change oxidation state. If anything changes oxidation state, then it is a redox reaction because that means we had an exchange of electrons. Now, if something is oxidized, something else must also be reduced. There's a reason we call these reactions redox reactions, and there's no such thing as just a reduction reaction or an oxidation reaction as a whole. Those two processes have to occur. So if something is oxidized, something must be reduced. If something lost electrons, they had to go somewhere. If something gained electrons, it had to take them from somewhere. So those two processes must always go together. So how do we label which is which? Well, when something is oxidized, it loses electrons. And when something is reduced, that means that it gained electrons. Now that can be kind of difficult to remember, so we have a couple of mnemonics to use in order to remember that. One is oil rig. Oxidation is loss of electrons, that's oil. Rig, reduction is gain of electrons, that's our rig. So oil rig. Oxidation is loss, reduction is gain. Another one is Leo goes grr, Leo the lion. So loss of electrons is oxidation, gain of electrons is reduction. So we have Leo and grr. It doesn't matter which one of those you use, they do the exact same thing. You use them for the exact same thing at the same time. Just pick one, use that one always for the rest of your life, and you'll be fine. Now, we say that something is oxidized or something is reduced. We can also refer to things in redox reactions as agents, and that is what they did to something else. When we say something is oxidized or is reduced, that's what happened to it. Or when they're referred to as agents, what did they do to something else? So the species that is oxidized caused something else to be reduced. So the thing that was oxidized, we say, is the reducing agent. In this reaction up here, we see that it is iron. We see that the iron lost 2 electrons. This is from our first reaction. So the iron lost 2 electrons. So that means it was oxidized, and it means it is the reducing agent. It made something else get reduced. So what got reduced? Well, the copper got reduced. The copper gained 2 electrons. I'm not going to be able to write that up there. And so it is the oxidizing agent. It made something else lose electrons. Okay, so the copper ion, Cu2+, is the oxidizing agent. Fe solid is the reducing agent. Your agents are always reactants. So that finishes out our introduction to redox reactions. As I mentioned, we will look at them in quite a bit more detail as we get into the chapter on electrochemistry in our very last lecture of the period. So hopefully you're able to watch all of these and everything makes sense. But of course, if you have any questions on any of the materials, please feel to email me or come to my office and ask questions. Good luck.